Okay, so this is Digital Signal Processing Demystified. My name is Amy Boyle, and that is my Twitter handle, if you feel so inclined to tweet at me. And what this is going to cover is, we're going to talk about who I am, why I was doing this, and first I'm going to try to define DSP. So it's Digital Signal Processing, it's a full acronym, but that's kind of a mouthful. So from here on out, I'm just going to refer to it as DSP. And then I'm going to give some examples of basic DSP concepts with sound, images, and data compression. We're going to learn how to filter out unwanted sounds from audio files and how to extract features from images. So I'm a software engineer at New Relic, but up until 6 months ago, I was a software developer for neuroscience research. So I was working in an auditory neuroscience research lab, so that's hearing research, so we're trying to figure out how the brain processes sound. So I ended up working with a lot of audio files, either trying to generate them or record them, and then manipulate them in some way to try to figure out how this affects the hearing system. So why am I giving this talk? One of the things is because I learned about DSP, and I just thought it was super cool. Signals are all around us. They touch a lot of different parts of our lives, especially in the digital age. And just having like a basic understanding of some of the concepts that form DSP, I think is really interesting. And if you want to get more into this subject and you don't know anything about it, it can be really intimidating. A lot of the materials out there assume you have a math degree, and if you don't, it can be hard to find the resources to kind of break in and start understanding the basics enough and have the vocabulary and to know what to search for. So I want to give you that starting point. Okay, so if you Google DSP and you look at the Wikipedia page, you'll be confronted by this definition. I don't speak Spanish very well, and this about makes as much sense as the English one did to me. I sympathize, though, with people who write this. I could edit it and change it, but it's a very broad subject. So you're trying to put a definition on something that covers so much, and it ends up sounding like you read that and you're like, yeah, okay, but what does it do? So I'm going to just try to define it here. And also, if you Google and you don't go to Wikipedia, you try to Google like a technique, you'll have this sort of phenomenon where the web page just seems to vomit equations at you almost immediately. And you're like, I just want, it's like, how do I use this function? I don't need to necessarily understand the entire underlying equation for this function. I just need to know if it's the one for me. So here's my definition. Take real-world continuous measurement, turn it into a discrete series of data points, and then use an algorithm to manipulate the data to do cool things. Or I'm going to make it shorter and reuse the acronym, doing stuff to points of data. Okay, so before we talk about digital signals, I just want to back up a little bit and just get us on the same page as to what do you mean by signal. This is a word we have all heard lots of times. What we mean here is some type of physical data that conveys information, so something that maybe varies with time or space. Examples being sound, which would be air intensity varying over time, light, which is intensity varying on space, so you have different light intensities for different, say, pixels in an image or photons on your eye. Temperatures varying with time. Heartbeats is electrical activity varying with time. And a hiking trail will be elevation varying with distance from the start of the trail. These are all signals. So a digital signal is when you take that signal and you turn it into points in time or space. We need to be able to hold this signal in computer memory, and to do so, we have to turn it into numbers. So we're going to need to discretize the signal, turn it into discrete points. The first step to doing that is to sample the signal. So sampling is going to give us kind of our x-axis values. We need to pick a time or space interval, and at that point, we're going to say, okay, what is the signal? What is the value of the signal here? And then we're going to do that for a regular interval at each time. So this will be like the labeling on our x. It might be milliseconds or millimeters. And then we also need to do it in the other dimension. So even if we have like a regular interval, we're sampling on the x-axis, we need to actually turn that possibly infinite valued data point into a number that's we're going to hold in computer memory. So this is going to depend on what number we're using. So if we're using an 8-bit int, we're going to have 256 different buckets that we can put this data point into. So we're going to look at this data point and say, okay, if I have 256 buckets in the range that I'm going to allow that my sensor lets me capture, what is the nearest value bucket that this value is going to fall into, and then we assign it that number. So we need to do both. And we need to pick a value, a resolution of sampling and a resolution of quantization that is going to be able to reproduce our signal reliably. And so this next figure is, in the top right, we have this basically what the signal looks like normally. We have a very high sampling rate, and we have a very high quantization rate. And as we go towards, to the left, along the top, we can see what happens if our sampling rate goes down. So this is when our points aren't close enough together. Basically, we have, for this point in time, we're assuming that this value that we've gathered is going to be the same for that entire time interval. And when that doesn't happen, we see that our data will at first look kind of like blocky, like it's an old video game. And then eventually, if we go too far to the other side, we kind of lose our signal shape altogether. Likewise, with quantization, so if we start from the top and we work our way down this grid, we'll see that when we put our value into a bucket, we're assuming even if we have like good sampling rate here on the right, we're grabbing points that are next to each other. These 3 points, we've assigned the same value, even though they have different values. And that will make our signal look blocky in a different way. And then if that's too bad, we eventually also lose our signal. And the bottom left is if you have both, and you can see that the bottom left looks nothing like the top right. So now that we have that signal in computer memory, anytime we do anything to the signal, that is DSP. So whether we're manipulating it, we're just analyzing it, that is considered digital signal processing. So that is why the subject is so broad. Mastering all of DSP is an unreasonable goal. And so it's good to get an overview and then focus on what area that you're interested in and you want to get at, because it's also quite a deep subject. One of the core principles of DSP is that all signals are a summation of sine waves. So I have an example here where I've added up all of the even frequency sine waves from 2 to 100 with decreasing weightings, and it basically approximates a sawtooth wave. So if you add all those together, etc., you get what's the graph there on the right. You can do this to any signal. So like some weird jaggedy looking signal that looks nothing like a smooth sine wave, yes, that actually is a weighting, can be a summation of sine waves. You just have to know what the right weightings are. This kind of blew my mind when I first realized this. I felt like that scene in The Matrix where Neo suddenly sees all the ones and zeros all over everything, only I'm seeing sine waves. I'm like, wait, everything is a sine wave? Yeah. And we're going to use this because we also have techniques where we can do the reverse and take a signal and figure out what its composition sine waves are. Okay, and I'm going to do this with a sound example. So this is a time series of a sound file. It doesn't look like much. Even if I zoom in, it basically just kind of looks like squiggles. I'm going to play it. Okay, so it's not a very interesting sound, but if we do a Fourier Transform on it, we're going to extract what the sine wave components are. So what frequencies or pitch is in the sound file. And if we do that, we find out that this is actually a two-tone. And I'm going to be using NumPy, SciPy, and Matplotlib in this talk. And that allows us to make this very easy because people have already written these algorithms for us. And the first thing I'm going to do is I've arbitrarily created this signal. So you can see that here that it's in fact just a two-tone signal because I've added two sine waves together. And then we're using NumPy to just run it through the FFT algorithm. So you stick the time series signal as the only input in. And we can also use a helper function to tell, which will give us our weightings out. And then we're going to use a helper function to say what frequencies those weightings are for, so that we can then plot it. And we see that this is the plot that you get out. So you can see that there's two tones there. That's very small, at about 750 hertz and 2 kilohertz, about of equal intensity. So this gives us just for the whole signal. It doesn't take time into account. So if we want to take time into account, we can generate what is called a spectrogram. And in this case, we're going to take our whole signal. We're going to chop it up into chunks. In this case, I've done chunks of 512 samples. And then we're going to line up those chunks next to each other. And we're going to use color to indicate intensity. This way it gives us both time information and frequency information with, of course, a trade-off of the size of chunk you use. And you can also overlap the chunks. So let's look at some audio that is more time sensitive, such as speech, because it matters what order the sounds come out of my mouth for any of this to make sense. So here's what this audio file looks like. Here's what
I say the whole world must learn of our peaceful ways by force.
Cool. So there was some distortion in that. Could everybody hear that high pitched? Yeah, it was unpleasant. I'm sorry. And you can also see it in the spectrogram. It's quite this big line across. So we're going to learn how to filter that out using DSP. So here's what the Python code looks like. After we import, we're just going to use SciPy to read in the WAV file. And then we need to establish a pass band and a stop band. So the pass band is going to be the cutoff for where everything below, we want to preserve those frequencies. And everything, the stop band will be everything above that, we want to get rid of it. And there's a gap here, so I said I want to get rid of everything above 11 kilohertz and keep everything below 10 kilohertz. There's a 1 kilohertz gap in there because I'm allowing for a transition. Because we can't go straight from one to the other, we can't have corners in our digital filter. And luckily for me, all of the distortion was above where the important frequencies were for the speech. So I can just safely get rid of everything above a certain level. I'm also going to get in what's called the Nyquist rate, and I'm going to talk about that a little bit later. But basically, I'm going to normalize those frequencies by my sampling rate. So I need to account for the sampling rate, that data rate we gathered it at, when I put the inputs into the signal function, the filter functions that are provided by SciPy. So I'm going to use a butterwheel filter, which is just a shape of filter. There are many others, but so I'm going to put in my stop band and pass band frequencies. I'm also going to tell it how much do I want to attenuate the stop band by, how much do I want to make sure that the bad sounds are gone, and how much loss am I willing to tolerate in the pass band of all the stuff that I want to keep. And I said I don't want to lose more than 3 decibels. 3 decibels is basically the smallest difference in sound that a human can hear. And I want to make sure that all the bad sounds are attenuated by at least 40 decibels. So this gives us our order and the normalized cutoff. So it does some math for us so that it figures out what parameters of the filter will give us what we need. It's how complex the filter is. So this is helping us figure that out, because you can have a more complex filter if you want to, say, increase the steepness of the cutoff, or depending on how much you need to attenuate or preserve your signal by. So then we're going to plug that straight into the actual filter function itself. It's called butter. I've got the B type in there, low. That means low pass. Low pass means I want to pass through all the low frequencies. There's also a high pass, which means attenuate the low frequencies and pass through the high frequencies, or a band pass, which imagine is going to pass through frequencies in the middle of a range. And this gives us out B and A, which are our filter coefficients. Now, if you look at the SciPy documentation for the signal package, you will notice that there is a lot of single literal variables, or very short ones. It's because it was written by mathematicians who love to do this. I've copied it here for the sake of a kind of matching, because then you can directly see where this is pulled from if you look at the docs. And also because the filter coefficients, their specific meaning is out with the scope of this talk. Just know that these are the 2 parts that make up the filter, and you can find these are what we refer to in math literature. But we can, I'm also going to create a new signal, an empty signal, to hold where the filter signal is going to go. And because it's stereo, I'm going to put the coefficients into this L filter, which is applying our function for applying our filter from the signal library. And then I'm going to write it back out to file. Okay, so this is a spectrogram of before, which you saw, and then after. So you can now see that the signal is gone. And if we play that file,
I say the whole world must learn of our peaceful ways by force.
So we did actually lose. You can see that there's all this complete loss of signal in the higher ranges, but because what we're hearing doesn't really matter in that range, that wasn't important to the speech in this file, we can safely just clear that out. And now we have our filtered signal. And that was all the code, right? There's one import statement missing, but that's how little the code that you needed if you are equipped with the right libraries that you need. Okay, I also want to talk a little bit more about sampling rate. So if you don't have an adequate sampling rate, so from that grid I showed you where the sampling rate was low, if yours isn't enough to capture the signal, you can have what's called aliasing. So here is a signal that I've generated that I've said I want a sampling rate of 500 hertz. I've used FS here also. That's another very extremely common two-letter variable. You'll see that always means sampling rate. So get used to it. And this is, I'm adding together a two-tone signal that's composed of 110 hertz and 120 hertz. And I've chosen a sampling rate of 500 because I know that's going to be high enough to get those signals in there. And sure enough, I run it through the FFT, and I can see that I've got the signals there in the plot in the end. However, if I chop that down and I have a sampling rate of 50, and I run it through the FFT, this is the only part of that code that changed, I see that now it looks like I've got 10 and 20 frequencies in my signal. And that's not true. I know that's not true because I just created this signal here. But if I was recording this from the wild, and I didn't necessarily know that those frequencies are in my data, I have now tricked myself into thinking that there's something there that is not. So this kind of and what you need is you need to have what's at least twice. If you have a frequency that is, say, 10 hertz in your signal, you need to have at least 20. It is double what the frequency is in order to get that frequency in the signal. And that is because you need at least 2 points per sine wave to be able to tell what those poles are. Okay. And this is kind of what that looks like. So the blue was the signal where I was sampling every 10 points, and the green is when I was separated with 500 hertz, and the green is when I was doing with 50. And the points are kind of showing how that aliasing was happening. So if you look at the signal, it looks like a nice sine wave, but really you've tricked yourself in by aliasing. CDs, for example, if anyone's ever seen that CDs are sampled at 44.1 kilohertz, that is because human hearing tops out at 20 kilohertz. And so you need to have at least double that, so you need to have at least 40 kilohertz. And there's also some headroom in there to allow for some filtering to go. So if they want to filter the data, there's room to have a transition. Okay. So now moving on to images. An images signal, it's a 2D signal, and it's in the spatial domain. So we're using space instead of time, kind of along our x-axis here. So if I took a chunk out of this picture here, which is of the waterfront in Portland, you'll see pixel values that are 0 to 256, and they might look like that. So if any of you use basic imaging editing programs, you might have seen those little sliders that are brightness and contrast. And what's happening here is you're basically changing the mapping of pixel values. So on the top row, this is the identity. This is a 1-to-1, no change. So if you have a pixel value that was originally 50, in the end you're going to have a pixel value that's originally 50. If you want to make it brighter, you're going to shift that up. So you're saying, okay, if the pixel value was 50 before, it's going to be 150 now. Likewise for all of the pixels up into a ceiling, at which point they get washed out. Likewise in the other direction for darkness. So this is what the code looks like. So we're going to import our image, and then before we do anything with it, even though it's a 2D signal, we're going to flatten it so that it's a 1D signal anyways before we do any data manipulation on it. But we're going to preserve the shape so that we can reassemble it. Then we're going to create that map. So we first create the map that's a 1-to-1, and then we're just going to shift it up. And then we're going to use that map and using NumPy indexing. Who here is familiar with NumPy indexing? Not that many people. Okay, so it basically, instead of just one dimension like regular Python lists, you can index things in 2 dimensions. So basically, we are going to take that mapping that we've now created that's shifted up, and we're going to use that to go back to our original map of our original image, and we're going to say, okay, and pull the index of we're using the second one, the writer. We're using the map that we shifted up to index into the original image in order to get the new pixel values. Okay. Which is actually what we're doing here. Okay, and then we're going to put it back into the correct shape. So it was flattened, now we reassemble it. And same thing for the darkness, only we're going to minus 100. Shift it down instead. Okay, contrast is, instead of changing the location of the mapping, we're going to change the slope. So what we want to do is, likewise, we're still kind of mapping, like, we're stretching the pixel values so that there's a greater difference between the pixel values in a certain area of the image. So this works well if you have a dark image that has a lot of difference between the dark colors. And our eyes can't tell the difference with a 1 pixel difference. So we want to stretch the difference in an area of the image where it's going to make a bigger difference to us. If there's a lot of pixel values that are very close together, it'll look like this. We're going to create a map just like we did last time, that's the 1-to-1. And then we're just going to multiply it by a slope factor. And we're also going to do the little brightness here because the brightness will actually shift the slope in the mapping. I've done it here so that it goes into the middle. And then we're going to make sure that we have cut off so that we don't have, because when you change the slope, it'll go out with the bounds of the 256. So we need to make sure that we're still, we've put the floor and ceiling on ourselves. Then we're going to, like last time we did with the brightness, we're going to use this mapping to index back into our original image to give us our adjusted image. And so this is using the function here that will be increasing the brightness by factor of 3, or we can reduce it. We can flatten it out and just kind of mellow out. This will kind of make the picture look more gray if it's a color image. We can do this automatically though, so that's doing it using the sliders, which when I use image editing programs, and I am not someone who's ever been good at that, it always just looks worse. But you can use histogram equalization, which is going to use the pixel values in the image where they're concentrated to stretch the pixel values in that region. So if there's a very dark image like this one, we'll get the pixel values and we're going to generate a histogram of it. So we're going to take all the pixel values and we're going to put them into bins so that we're counting all, like what are all the values, like how many pixels are there that have the value of 5, the very dark color. And this one, there's a lot. There's a lot very concentrated in the dark end of the region. There's a little bump here for that little frog that was very light. And then we're going to take the running sum of this histogram to get our map. So this is just like those maps that we were looking at earlier, only this one's not linear. And so then we use this mapping just like we were doing with to index back into the original image. And this is just, right here's all the code just together. And what we get is we can now see a lot more differences in the image. So you didn't realize before that there were ninjas hiding in this image. But in fact, when we stretch the contrast in the area where most of the pixels are, we can now see them because we've given our eyes a big enough difference to notice. Of course, this is kind of a common thing to do. So someone's already written a library function that does that, and so here's what it looks like in color. This was from the pillow fork of the Python image library. It just has an equalize function, so you can just call that, and your picture looks magically better. Well, it's not magic, now you know how it works. Okay. So the last thing I want to talk about is data compression. This is great because it's actually going to use some of the concepts that I've already talked about in the rest of this talk and apply them in a different domain. So I'm specifically going to talk about JPEG, and this stands for Joint Photographic Experts Group. And that doesn't really have anything to do with it, but it's nice to know the acronym. And one of the interesting things about this is JPEG is a compression algorithm, not a file format, which would be a common misconception because a lot of images end in like that JPG. But what they actually are is probably EXIF files or JFIF, or probably JFIF files, but maybe also EXIF. And information is basically contained in the header to say what kind of file format they are, and also information about the algorithm. And here's the overview of the algorithm. First, you're going to convert from color spaces. I'll explain what that means more, but then we're going to downsample. We're going to basically just throw out samples. We're going to run the DCT, which is the Discrete Cosine Transform, which is very similar to the Fourier Transform that I was talking about earlier, although it focuses on cosines instead of sines. Then we're going to quantize our data and encode it. So one of the important things about this is an image compression algorithm. It is a lossy form of compression. That means we can afford to have, when we decompress the data, it may not be exactly equal to the data that we started with. With the case of things that we perceive with our human senses, this is okay. Because if it's a little bit worse, if it was really high res, and maybe your eyes cannot detect the difference. And we're going to take advantage of that here. So the first thing that we're going to do is we're going to convert from RGB to YCbCr. And what that is, RGB you're probably familiar with. This is how monitors represent color. You might have dealt with it when you're programming. It encodes how blue, red, blue, and green the image is. We want to convert to YCbCr, which tells us what the luminance of the photo is, and then blue and red, basically. And this is important because we want to preserve the luminance much more than we preserve the blue or the red, because that is way more important to our eyes. We see luminance much more than we see blue or red. And I tried to illustrate this with these images here. The red one actually looks pretty good, but that is because I was just using standard color maps, and any good color map will actually go from light intensity to dark intensity, or vice versa, so that because that's how our eyes work, and they want you to be able to see the difference between the colors in the color map. So this red color map actually, the reason you can see that image so well is because your eyes are picking up on the intensity. And of course there's functions for that. So this next step is actually an optional step. So you can downsample. So we're just going to take those blue and red color domains, and we're just going to drop samples from them. We might drop 3/4 of the samples from those data layers. I say this is an optional step because also in the header data, you're going to describe what you did at each step. So you're going to say whether or not you downsampled at this step and by how much. So that when the image is reversed, when you want to take it out of the, decompress it, you can reverse the steps. So the next step will be to divide the image into 8x8 chunks. And the reason for this is actually for legacy reasons. For hardware was the kind of limit that DSP hardware had at the time. And so we're just going to loop over all of the 8x8 chunks in this image of Grasshopper here. And then we're going to, so this is what I taken a grid from this overall image, and I've shown you what the pixel values are. So they're from 0 to 256, but we actually want to shift them to be minus 127 to 128, because this is what the DCT algorithm expects us to be into, because they want them to be around 0, so we can figure out what cosines they are. And then this is the hard part, conceptually anyways. So what we have here is there's an image. The image on the right is our original block, and the image on the left is actually, it's an 8x8, but it's also, each tile in the 8x8 is made up of 8x8 squares. So what we're not doing is a one-to-one correlation. What we want to do is we're going to take each of those little tiles, we want to say, how much is our chunk of data similar to this particular tile? And we're going to give it a weighting. So we're going to say that is a value, for a higher value means our image is most like, for example, a checkerboard in the bottom right, or it is not like a checkerboard at all, and we're going to assign that to 0. On the other hand, we're saying, oh yes, this is very vertical, stripy image, so we're going to have a high value for that little tile. And on for each tile in that 8x8 grid, we're going to have a value that represents how much our data block is like that pattern. There will always be a number for the top left, because that is basically the overall shade of the image. And so this is a two-dimensional object, so we run the DCT on it for each dimension. And then we end up with this grid of coefficients. So that gives us one number for each of those tiles. And oftentimes it works out that there are bigger numbers in the area where there was less pattern difference. So that checkerboard there in the bottom right is like, it's a 1-by-1 pixel difference from light to dark. Most images are not like that. That's at the eye level where your eye really has trouble seeing. So there's two things there that's quite rare. And also, we can't even really see that difference. So we're going to take advantage of that and use it to basically throw that data out, depending on our compression ratio. Because in this step, we're going to take all those coefficients that tell us what our image looks like, and we're going to divide it by some number. So this, which is the grid in the middle. This is the quantization table. We're going to make this up ourselves. And we're going to put this 8 by 8 numbers into our header data specifically. So we can pick any numbers we want here. And the higher the number, the more that we're going to reduce that coefficient by. So this is a 1-to-1 application. So these are very tiny numbers, but there's a 4964 in the ECT coefficients. We're going to divide that by 16, and we're going to get 310. We're going to do that on an element-wise basis for each number. And what we've done here, which is very common to do, is to have bigger numbers towards the bottom right. And this means that we're going to compress these detailed patterns, the one with the bigger, the smaller, more detailed differences, by a larger rate. And in fact, what we want to do is we actually want to end up with 0, because we're going to round to the nearest integer. And in this case, you end up with a lot of zeros in the bottom right. This is exactly what we want. Because in the next step, whoops, quickly go over the steps that I've been over so far. So we have our original image. We get the pixel values for the image. We shift them to be about 0. We run them through the DCT so we get the weightings of what the patterns are like. Then we divide it by a number that we've chosen to weight it to reduce the numbers in the quantization table. Sorry, to reduce the DSP coefficients. So we get a lot of zeros. And then we're going to apply Huffman or run length encoding. So I'm not going to go into the details of this algorithm since it's not within the scope of this talk, but basically we want all those zeros in a row because we're going to take that grid now and we're going to zigzag from the top left where all our big numbers are to the bottom right where all those zeros are. So that when we get the numbers in a line, we have all those zeros in a row so that instead of taking it memory going 0, 0, 0, 0, 0, 16 times, we can go run of zeros, 16. And now we've saved a lot of data. So this is a side-by-side image of a PNG file, which is a lossless data file, next to the JPEG of the same file that I ran this image through. And one of these files is 10 times bigger than the other, and I bet you can't tell which one is which. The code's online if you want to check. Yeah.
Where?
I will tell you at the end. Because I'm nearly done. So some of the things I want you to take away is remember the DSP is just doing stuff to points data. Signals are composed of sine waves and can be decomposed into them. Adequate sampling rate is important, so understanding what data you're capturing or generating, just the domain knowledge is important to make sure you don't experience aliasing. That's understanding the underlying process. So here's what the stuff is. I have these presentation slides on my website, which is amyboyle.ninja. Yes, .ninja is a top-level domain. Yep. .com was taken, so you know. It's a very professional website where I take pictures of toy ninjas. But I do also have a few other blogs on this, blog posts, where I go into a little more detail. I have some fundamentals talks where I put in stuff that I didn't have time for here. And I also go into more detail about some of the audio filter work I did at my previous job. And the source for this talk, the slides, and basically all my working source is on my GitHub, which is there, Boyle/DSP talk. And I have a bunch of, you can see I've made all the graphs in this talk, and you can see how I made those graphs in IPython notebooks, which you just learned about if you were in this room. I will warn you that they are not very well annotated, so it's a bit like looking at my messy desk with all of my notes spread out on it, but the code is there and it runs. Yeah. And so at this time, I will be taking a break with us. Yes.
I had an idea around application. You kind of changing your voice, but actually making it sound like another person's voice or a cartoon character.
Mm-hmm.
Is that very hard to do? Is that doable? You have to be a mathematician.
You do not have to be a mathematician to do that. That is a form of audio processing. Basically, you're just going to try to shift the pitch up or down. I've done this, so it's just getting a little more familiar with the audio processing side of it. I have a great book to recommend for that. I used The Scientist and Engineer's Guide to Digital Signal Processing extensively when I was learning about DSP. It's especially great if you don't have a super strong math background. It does go into more detail about like how the Fourier Transform works and stuff like that. If you want to read the whole book, it's really interesting. But it does have some more sections on audio processing, and it'll should give you the kind of background you need for that. The Scientist and Engineer's Guide to Digital Signal Processing. It's online for free. You should get it if you Google that. I think I probably linked to it on my blog as well.
Read the link right now.
Awesome. Yeah.
The first one is DSPguide.com.
Oh, DSPguide.com. Yes.
Yeah, I don't know if you know the media computation approach to speech programming, written by Marcus Dial. It's something like your talk, but for a very low level. It's not more or less the same. Teach programming, using and manipulating pixels, manipulating waves, sound waves. I don't know, but I think that this approach is very nice, but I didn't like that. I don't like that they use only Java tools. They call this Python, but all the practices, the lectures, use Java tools to play sounds and.
Yeah.
I don't know. The point is. You're thinking or to make, I don't know, you're thinking about the possibility of downgrade the engineering content of this kind of talk to give massive spreading of this idea. But it's very cool that I think that has a very narrow people audience.
Okay. Thank you.
You can do audio processing in Python.
Yes.
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 I know.
So the reason I used Python in the first place was because I got to choose to use Python, actually. I was working in the lab and starting a brand new project, so I had to have, and my professor gave me free reign. So I looked at what was out there, and I saw all the great scientific libraries in Python and the great tools, like Python Notebook, and I said, yes, this is the language I want to use, because it's a high level, so you can kind of work quickly and throw stuff out and not feel bad about it. And there's a lot of really good libraries that do the functions for you that actually run pretty fast, because underneath they're running on Fortran. C. Yeah.
Yes, you were telling us that an image is like a group of pixels that you can read in the PC read like an integer, right? What occurs when you expand the image?
What happens when you expand the image?
Yes.
Like if you zoom in, in your
Yes,
browser or
okay,
something?
close enough.
So, yeah, depending on the resolution of the image, you're just going to get closer so that you can actually see the difference between the pixels. Or if you're zoomed in past the point of resolution, depending on what program you're using, it's probably just going to assign that single pixel to actually a larger amount of pixels on your monitor. Does that make sense?
Yes, but if you do that if you don't have a good resolution of the image, you lose the quality.
Yes.
But when you, I don't know the correct word in English, vectorize?
Yes, vectorize, yeah.
Okay, when you vectorize the image, what the program do? Because you doesn't lose the quality of the image. When you
It's very different. You don't represent by pixels for geometric objects.
It's more like capturing the image with equations and functions versus
Yeah.
pixel, like a grid.
Doesn't ask you to use
shapes like polygons, like points and lines, rather than like pixels?
Yes. Yes. So that.
I mean, when you scan an image, your computer guesses which pixels from the image to assign to which pixels in the monitor. Even your straight line, if you look very close, it's going to be really crooked. If you look really, really, really close, there's an algorithm that you use to interpolate a straight line on a pixelated screen.
Yes.
So let's say the audio for my presentation is really bad. Will I be able to write Python to improve the signal quality? Let's say if it's just because there's too much ambient noise.
Potentially, it depends on where the ambient noise is, but you'll probably be able to apply some techniques. If it's in a frequency range, high range, yes. There are also other techniques that you can use to try to pull out the frequencies that you're specifically interested in, or a certain type of regular background noise you can get rid of.
And something that I read is that you can actually, if you have two microphones, you can record your voice from two sources to microphones. You can actually find a common thing between those two audio waves.
Yeah.
And filter the other things.
Makes perfect sense.
Yeah, that's how phone works, so you don't
Like
have
the-
to, so the noise doesn't get you as well.
Yeah.
That's everybody problem.
Okay, Amy, I hope you were recording from your computer too.
Yep. Okay. Thank you.
So good.